Okay, so now we're going to learn how to solve for inverse Laplace transform. So this is kind of like when we first learned antiderivatives, we can only do so by guessing. So let's do an example here. Suppose we want to find the inverse Laplace transform of the function 1 over s cubed. We first, by making our guess. So 1 over s cubed appears in here, kind of. And the alpha value is equal to 2, so our guess will be t squared. So if we actually find the Laplace transform of t squared, we'll realize this is equal to gamma of 3 over s cubed. Gamma of 3 is 2 factorial, so it's 2 over s cubed. So the Laplace transform of t squared is not 1 over s cubed per se, but we can divide by 1/2 on both sides. We can divide by 2 on both sides. So we get the Laplace transform of t squared over 2 is equal to 1 over s cubed. And therefore, the inverse Laplace transform of 1 over s cubed is t squared over 2. So let's do a different example. So suppose we want to calculate the Laplace transform of 2s minus 6 over s squared plus 9. So the denominator s squared plus 9 indicates this one of these two terms, or both of these two terms. So let's first split it into two fractions. So it's the Laplace transform of 2s over s squared plus 9 minus the Laplace transform, inverse Laplace transform of 6 over s squared plus 9. So we know according to the chart, the Laplace transform of cosine 3t is equal to s over s squared plus 9, and the Laplace transform of sine 3t is equal to 3 over s squared plus 9. So we want to make these two terms happen. So let's factor out the unnecessary constants. So for the first one, let's factor out 2. So we get 2 times inverse Laplace transform of s over s squared plus 9 minus, for the second one, we want 3 to remain in the numerator. So let's factor out 2. So it's equal to 2 times the inverse Laplace transform of 3 over s squared plus 9. Now, these two exactly match the thing we have on the right. So this is equal to 2 times cosine 3t minus 2 times sine 3t. Okay, so this is how we find inverse Laplace transforms. First by guessing. So guess first, and then scale by the correct constant. Okay, so let's talk about some general theory for Laplace transform. So we have to first talk about the definition. So we say the function f of t is of exponential order as t approaches infinity if there are constants c and m such that f of t is bounded by m times e to the ct as t approaches infinity. So in some sense, this is being of an exponential order as t approaches infinity means that f of t does not grow faster than exponential function. Luckily, most functions we care about satisfy this property. So we don't have to worry too much about this. Satisfy. Okay, so given this definition, here's some general theorems. So the first one is if f of t is of exponential order as t approaches infinity, then the Laplace transform exists for s greater than c. The c here is the c coming from the constant up here. And the consequence of this is the limit of the Laplace transform as s approaches infinity is 0. This is a very powerful property. This tells us which functions can be coming from Laplace transforms and which functions cannot. For example, because the limit of s over s plus 1 as s approaches infinity is 1, not 0, so the function s over s plus 1 cannot come from a Laplace transform. Yep. Therefore, the inverse does not exist. Now, the third property is what guarantees the inverse to be unique. So if f of t and g of t are of exponential order as t approaches infinity, and they have the same Laplace transform, then the original functions must be the same. So the third property tells you that inverses are unique. Okay, so that's it for section 10.1, and we will talk about how to use Laplace transforms to solve differential equations in the next section.